This video is the first example for doing a bolted steel connection. And I've got two plates here. The upper plate and the lower plate are both 1/4 of an inch thick, and both plates are 2.5 inches wide as shown in the diagram here. These two plates are connected together by two A325 A bolts that are 3/4 inches in diameter. Both of the plates are A36 steel, and we're going to assume that the hole types are just standard holes that these are going through. The load being applied here is applying a shear force on the bolts, and let's go ahead and check the connection. This video actually follows the previous conceptual video that went through the equations, so I won't spend a lot of time talking about the equations, but if you do need to go back and reference what the equations are and the terms that are in there, need a little more help with that, maybe what the diagrams of the failure mechanisms look like, refer back to the other video. In this one I'm just going to plow forth on the math and show you how to do that. I am missing one key piece of information on here. The load that we're applying to this particular connection is 10 kips. So we've got 4 different failure mechanisms that we need to check, and we're going to start with our bolt shear. Alright, the bolt shear equation, if you recall, is the actual stress for bolt shear is equal to the load divided by the number of bolts times the area, and all that needs to be less than or equal to the allowable shear stress. So let's go ahead and plug these values in. We've got 10 kips is the load that's acting on this connection. We've got 2 bolts within the connection. We need the cross-sectional area of the bolts, so we could do pi r squared, or pi times diameter squared over 4 will also give us the same number. So pi times the diameter, 0.075 inches squared, don't miss that, divided by 4, run that through our calculator, and 11.3 KSI is the actual shear stress that this particular loading causes. The allowable shear stress we can simply pull from table 10.1, and so if we go into that table, make a note of that real quick. From table 10.1, it's the A325 Class A bolts with a standard hole, and you'll find on there it has the shear stress value, or the allowable shear stress value of 17.0. We compare those two values. Our actual is less than our allowable, therefore we sing "Oh Happy Day" and move to the next one. We also need to check our bearing capacity. Failure mechanism number 2. Recall the bearing capacity equation. F sub P equals P, the point load, divided by N T D, and all of that has to be less than or equal to the the allowable bearing stress. I'm going to go ahead and substitute what that value is. If you recall, it was an equation that we had to calculate. This one right here, if you recall, was the area for bearing, and this one right here was the allowable bearing stress. Again, you can go back and look that up if you need to. We'll make one additional note here. We've got to go clear back to table 5.1 in the textbook when we were talking about material properties, and we can find that for A36 steel, we've got an ultimate stress of 58 KSI. And we do need that value for this math. So let's go ahead and start plugging our values in. The actual bearing stress is equal to the 10 kips. We've got 2 bolts. We've got a 1/4 inch thick plate, and both plates are the same, so we only need this calculation once. And we also have a width of a bolt diameter of 0.75 inches. Apologize, I said that wrong. Run that math through and we get 26.7 KSI. And we still got to do the other side. The allowable stress is equal to 1.2 times our 58 KSI, which gives us 69.6 KSI. And we can see that our actual bearing stress is significantly less than our allowable bearing stress. Whoops, I just put a B instead of a P. And therefore this case also works, and we know that we're good for bearing. All right, next one. We need to check the tension on the gross area. So we've got the gross tension equation equal to the point load divided by the gross area, which is the width times the thickness. This is the gross area, or A gross. And all of that has to be less than or equal to the allowable tension. We'll go ahead and just substitute that in. And it's 60% of the yield stress. That's what gives us our allowable tension for the gross area. One other quick note here. We do need the yield stress, and for 36 KSI still, I don't like the way that looks. Erase. For 36 KSI still, the yield stress is 36 KSI. All right, time to plug some math through. The gross tension actual is equal to our load, 10 kips, divided by our width. Width is 2.5 inches, and our plate thickness, 0.25 inches. Again, the plates are the same, so we only need to check one condition. And we get a value of 16 KSI as our actual stress. Our allowable stress is equal to 60% of 36 KSI, which is 21.6 KSI. Compare actual to allowable, and we can see that we are less than or equal to the gross value that governs this particular case. Therefore, this connection should be okay for a gross tensile failure, meaning all the way through the plate. All right, one additional value that we need to check. It's similar to the last calculation, but we need to check tension on the net area, and that's simply code for at the connection. In other words, going through one of the bolts. If we were to come back up to our diagram really quickly, we could fill this either here or here, and you'll note that each of those is the same, and so we only need to consider it once. but we need to go through the weakest point if somewhere is smaller than the others. This equation is just a little bit longer than the others, but the actual net tension failure, net tension stress equal to the point load. This is how we get our width minus the bolt diameter there multiplied by the thickness. All that's got to be less than the allowable tension stress for this condition, which is 50% of the ultimate. And so just as a quick reminder, this is the net area. This one right here is the allowable stress for net tension. All right, time to do some math. Oh, I think we did we do this one already? I don't think we have done this one. We do need to go back to table 5.1 and remember that the ultimate stress is 58 KSI. All right, time to do some math. FT net equals the 10 kips divided by, all right, we've got 2.5 inches as our width. We've got one bolt. So we'll go ahead and put one bolt right there. And that's multiplied by the bolt diameter. Now remember, the hole's got to be at least a 1/16 of an inch bigger than the bolt diameter. So I'm going to add a 1/16 of an inch to that. I had to do this on my calculator to figure out what a 1/16 of an inch looked like in decimal form. But 1 divided by 16 is 0.0625 inches. And that gives me my area net. Multiply that by my plate thickness. A lot of math down there on the bottom. And we run that through our calculator. We will see that the actual tensile stress on the net area is 23.7 KSI. All right, final piece for this whole problem. We need to compare it to the allowable, which was 50% of the ultimate stress. Go ahead and substitute that in, 58 KSI. Run it through our calculator. If you're smart enough to do it in your head, you can do that one in your head. And we get 29 KSI. Let's compare it real quick. FT net, again, is less than our allowable tensile stress. And so in our final case, it also has sufficient capacity. All right, just to recap what we've done here. We've got our connection. We check 4 different failure mechanisms. For bolt shear, we've got sufficient capacity. For bearing along that bolt cylinder and inside the hole, we've got sufficient capacity. In fact, we've got way more capacity than we need there. That one's usually not one that's going to fail. For a plate failure, sometimes we call it a block shear going all the way through the plate. We've got sufficient capacity. And for a tension failure that would go through one of the connections, meaning one of the bolt holes, we've also got sufficient capacity. Because all 4 failure mechanisms have adequate capacity, this bolt connection has sufficient capacity and should be good for the 10 kips, which needs to be placed on this particular steel connection.